polar form of complex numbers. So first, let's start with definition. Polar coordinates. Well, the polar coordinates is invented by Isaac Newton. Consists of point O called the pole and the horizontal line or horizontal half line, right? Emanating. Sorry, it should be radiating. I think the textbook is incorrect. It should be radiating from the pole is called the polar axis. So, and now let's introduce another form, theorem. The polar form or polar representation of the complex number Z is defined as Z is equal to you have R, and then you have cosine theta plus I sine theta, right? So this is the polar representation. And let the modulus of Z be defined as R equal to Z, right? So this is the length, right? And then we should start with definition. The angle of inclination theta, inclination of the vector Z will always be measured in radians, right? And the angle theta is called the argument of Z. It's denoted by theta equals to argument of Z, right? And an argument theta of a complex number must satisfy the equation such that maybe blue, right? That is cosine of theta is equal to x over r, right? And sine of theta is equal to y over r. Well, that is, if you draw a triangle like this is a theta, right? This is argument of z. Start with this notation. Now you have xy, and z is equal to xy, right? And then you have y, you have x, so it must satisfy this triangle, you might think, right? And an argument of a complex number z is not unique since cosine and sine are 2 pi periodic. In other words, if theta naught is an argument of z, then necessarily angle theta naught plus 2 pi or plus 4 pi, right? That is equal, so that is theta naught plus, 2n pi, right? That is the period. Is also equal to the argument of z, right? However, tangent of theta is pi periodic, so we must take care of, we must pay attention to it. So now, let's do an example, please. Example 1, right? Example 1, so let's express, z equals to negative root 3 minus I, right? Minus I, like that, right? So, z can also be written in x, y coordinates form, which is equal to negative root 3 and negative 1, right? And since we know r is equal to the modulus of z, we can just perform the calculation, the root calculation, right? And we can square negative, square of negative root 3, right? Square, and then plus, you have negative 1 square, right? That's equal to, that is really just, we square this is negative 3, that is equal to square root of 4, that's equal to 2. So now, y over x is equal to negative 1 over negative 3, that is equal to 1 over negative 3, the negative cancel out, right? And then we want to find theta, right? Theta is the argument, so we say argument z is equal to theta is equal to arctan of 1 over root 3, that is equal to pi over 6, right? But since you have to pay heed on this one, xy, right? We have to know this is equal to negative 3, negative root 3 and negative 1. That is in the third quadrant, right? So you have to make it negative, right? Really, now tangent of theta, right, is equal to negative 1 over negative 3, right? You can think of like that, and it's equal to negative 1 over root 3, right? So we now say theta is equal to the argument of z is equal to pi over 6, right? But you can also add pi because tangent is pi periodic, right? So period is pi, so now you want to move it over here because this is pi over 6, right? You want to move it over here, you want to add pi, right? So this is equal to 7 pi over 6, right? So now we may conclude our answer. Our z is really just, what is our r? Our r is 2, and then we have cosine of theta, right? Cosine of theta, that is 7 pi over 6, right? And then plus imaginary number sine 7 pi over 6, right? And that is our answer. That is correct. And now a new theorem. No, actually, maybe a definition. New definition. right? The symbol argument of z, right, actually represents a set of values, but the argument theta of a complex number that lies in the interval -1, negative pi less than, that is argument represents a series of number, but the the value, the complex number, the argument of theta that lies in negative pi, or maybe like this, maybe this notation is better. Theta is element of negative pi. Note that it is not inclusive between negative pi and pi. That is called the principal value of argument of z, right? Principal value, right? Or the principal argument. I think we should call it principal argument. The textbook says both. Well, that is negative pi. Well, that is right, of z less than pi, right? That is, the principal argument lies between these two values, these two angles. Well, maybe also add denoted by argument of z, right? And note that this is capitalized, right? And this is not capitalized, right? There. So for example, maybe a short one, example 2. Well, we see that if z is equal to I, right, and that is z is equal to, 0, 1, right, and r of 1 is just 1, right, and really there's no increase, so you may see the triangle as like this. So it will be infinity, right? So perhaps this doesn't work. 1.9. Curious. If z is equal to I, then no. I think there's something wrong with the textbook, but well, let's skip it. Maybe we can do number 1 again, right? There's something wrong with the textbook. Maybe -3 minus I, right? We know the polar representation is this number cosine of 7 pi 6, right? And then plus I sine of 7 pi 6, and we know that 7 pi it is greater than negative pi and pi, right? Because that is basically 6 pi over 6 plus 1 over 6 pi, right? That is greater than pi. There, right? And this is equal to argument of z, right? So we say the argument of z, which is this number, it is equal to, we can just subtract pi, right? So that is equal to pi over 6, right? Which is over here. right? And now, let's see. If z is equal to I, right, that is our xy is equal to, well, really just 0 plus I, that's 1, right? And r is equal to 1, r is equal to 1, let's see, really it's just this, you know our y is equal to 1, right? And r is equal to 1. How's that possible? Figure. Well, maybe you can start from drawing, like the polar axis, right? We have x and y, really, well, Cartesian, but now we want to write it in terms of, polar axis like this, So now we have I over here, this is I, right? And what is I? We can do pi over 2, right? So this is equal to, well, pi over 2, right? And then we can do it again. That is, well, sorry, maybe this way. If we go from the other way, right? That is equal to, well, this is negative 3 over 2 pi, right? No, negative 3 pi over 2, right? We can do it like that, or we can even go 360, go back to it again. So this is, well, 5 pi over 2. So we know, we know the argument of I, right, of z equals to I, right, is equal to, well, we have pi over 2, really, we have pi over 2, we have 5 pi over 2, and we have negative 3 pi over 2, right? Well, so the argument of, the principal argument of z equals to I is equal to, well, pi over 2, right? We want to pick that, okay? And because it lies in negative pi and pi, right? So, well, let's see. Could we find a polar representation of this? Well, I think so. Well, it's x over r, but x is 0, right? So let's see, we have y over r and x over r, right? And we know that this is cosine, right? And this is equal to sine. Oh, sorry, flipped it around actually. This is sine. I should have known better. And this is cosine, right? Right? And what is our y? Y is 1, right? So we have sine of 1 over 1, and then x is 0, right? Because, well, this is a triangle, really this is 0, 1, 1, so it's actually a line like this, right? So maybe x is equal to, 0, so you have cosine of 0, right? So I think the polar representation can be written as, z is equal to, well, r is 1, and you have cosine of 0, that is 1, and you have I of sine, maybe sine of 1, right? Something like this, right? If you have 1, you want to shoot up, right? That is when sine is equal to 1, or actually, sorry, forget about this thing, right? Forget about these. Really, we already have what we need, right? So this is equal to r, and then cosine, that is cosine of, pi over, what was it, pi over 2, plus I sine of pi over 2, really this is just equal to 1 times 0 plus I. So I see, I was confused. Now we may come to a corollary, right? That is the relationship between argument of z and the principal argument of z can be written as well. That is really just argument of z, right, is equal to really just the principal argument of z plus the cycle, right, to n pi for for n that is all integers, right, and an element of integer, right? And well, let's define definition. Let's define the multiplication and division, right? The operations on arguments. So I think it does qualify as some sort of weird vector space, but we shall see. So we have multiplication and division. So the polar form of a complex number is especially convenient when multiplying or dividing two complex numbers. Suppose z1 is equal to r1 cosine of theta 1 plus I sine theta 1, and z2 is equal to r2 cosine theta 2 plus sine theta 2, right? I sine theta 2 there. So, well, then the multiplication and division of arguments can be defined as, well, that is argument of z1, z2 is really just equal to argument of z1 plus argument of z2, and the fraction of z1 over z2 is equal to argument of z1 minus argument of z2, right? And now we want to prove it. Okay, well, suppose we have already supposed it right here, right? So now, well, how about we do the product, right? We do the product, that is z1 multiplied by z2, well, that is equal to, well, if you multiply them, you have r1, r2 on the outside, right? And you have cosine of theta 1, cosine of theta 2, minus sine theta 1, sine theta 2, plus, well, now we do the imaginary part, well, sine of theta 1 cosine theta 2 plus, well, cosine theta 1 sine theta 2, right? So this is after grouping terms, so you can really just write out, you can write r1 and then cosine and then sine r1 sine and r2 cosine I r2 cosine 2, right? Like that, you can multiply it, and then you see the imaginary parts over here, they they really just created this part because imaginary square that is negative, right? So that really makes sense. So if you can multiply it out, right? But that is only if you want to, and that is so. Now let's continue with our proof. Really, you can just write this as maybe just equal to, well, R1 and R2 doesn't change, or you can really just use the angle sum formula, right? Really, because just remember this. Sorry to sing this, but I must. This is how I remember it. You have sine A plus B, right? Pretend there's a bracket over here, right? A plus B. So this is equal to sine cosine sine cosine minus sine, right? That's how I remember it, right? Because if it's not specified, then it's addition, right? So sine cosine sine cosine minus sine. Wait, sorry. Sine cosine sine cosine minus sine, like that. Really, that's how I remember it. Now, so right, so this is cosine minus sine, so that is plus, right? Now you also have imaginary part, that is, you use the sine cosine sine, right, like that. So that is equal to, but note that this is a plus, right? So that is plus, right, like that, right? So, well, this can be really written as well, if you would distribute it, right? Wait, no, actually you don't, because well, that is just really, you just add the two, really, I think, right? Well, now actually we have so this is a product, right. If you add it, right, these go together, and then you really just have to add it, the sum of the angles, right? Really, they get enlarged. Right, you have something like this. Sorry. So if you have, let's say, I think it would be better if I draw the figures. This is Z2, right? And you have Z1, right? And you have, this is, sorry, maybe like this. This is theta 1, this is theta 2, right? And now pretend we do add the magnitude together, really. This is, well, now how about we do the angles first, right? So this angle plus this angle, or it should be this angle right here, right? Oh, sorry. It might look a little bit off, but just pretend this is bigger, because it wouldn't make sense if I draw over here, because now it will look too small and it's not so clear. But actually, just pretend I drew a little bit bigger, but it's really the sum of the two angles, right? Now if you would draw like this, right? Right, maybe longer, like this, right? This is Z1, Z2, really. This is really what happened when you multiply it, right? Really, because look, if you do multiply it out, right, you have argument of, you have argument, right? And if you multiply it out, well, let's just do it. Come on. So you have cosine theta 1, R1, R sine theta 2. No, 1. Sorry, this is R1. Now this is R2 cosine theta 2, I R2 sine, really, you do see there's this product over here, so therefore you can always factor it out. That's where this term came from. And you have these, really you just multiply out. So I think that's just all the arithmetics. Right, now I just want to clear this. There. So now let's continue the proof. Now pretend I did all the arithmetics correctly, so I won't show that much work now. Really, pen, there. Now just do the arithmetics. I won't do too much explanation. We are running out of time. Right, so this is equal to R1 over R2. Sorry, maybe some extra steps. Well, you get R1 over R2, and you have cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2, right? And then the imaginary part, you have sine theta 1, cosine theta 2 minus cosine theta 1, sine theta 2, right? What did I do? There, right? And well, that is actually equal to, so if you do the simplification with the sum formulas, angle sum formulas, you'll get cosine of theta 1 minus theta 2 plus imaginary part sine of theta 1 minus theta 2, right? And well, this is just equal to really just argument of z1 minus argument of z2, and this is argument of z1 plus argument of z2, and that completes the proof, right? And now let's do an example just to prove this. Just to verify it, we've proved it, and now you have example 3, right? Well, perhaps we have z1 is equal to I, right? z2 is just negative root 3 minus I, right? And well, we know the argument of z1, that is equal to pi over 2 principal argument, but I would just refer as argument. You just look at my notation. If it's capitalized, then it's principal argument, right? And then you have 5 pi over 6. Sorry, I missed the 5, right? And well, if you do multiply it, right? So z1, z2, that is equal to I multiplied by negative 3 minus I, that is equal to 1 minus root 3I, right? And if you do the division, right, that is equal to I over negative 3 minus I. Well, if you would recall what we've done last round, you multiply by the conjugate, that is just negative 1 over 4 minus the imaginary part, negative root 3 over 4 I, right? And now you want to combine them, so now you have argument of z1, z2, well, that is just equal to argument of each of them. So that is equal to, well, first one is pi 2, and then you add the minus, right? That is 5 over 6 pi, right? You have pi up there, and then that is equal to negative pi over 3. And the argument of the fraction, that is equal to first argument minus subtract the second argument, really that's 5 pi over 6, and that gives us 4 pi over 3, right? And now we want to introduce a new theorem, right? So, new theorem. Okay, very well. A theorem. Hopefully I didn't just destroy anything. No. So now, right, theorem. integer power of z. Okay, so we can find integer powers of a complex number z from the result in the previous theorem. For example, if we have, well, how we do the example later, and then so I will instead just summarize the textbook. The power of a complex number z, the nth power of a complex number z can be defined as the following manner. Can be defined as the following manner, that is z to the nth power that's actually equal to r to the nth power, and that is equal to cosine of n theta plus I to the sine n theta, right? So sorry, I will just give a brief proof about this. There's no proof in the textbook. Well, the approach can be written as, well, really we can define z1 is equal to z2, right? And z1 multiplied by z2, that is equal to z1 z2. No, that's z1 z1, that's equal to z1 square. So we can use the argument of, principal argument of z1 z1, that is equal to argument of, well, z1 plus argument of z2, right? Like that. Okay, and well, and that is really just the argument. No, but I don't think this is relevant over here. Actually, sorry, we can use a polar representation, right? We can do maybe we have z1 is equal to r1, sorry, maybe just r cosine of theta plus I sine of theta. You multiply that by you multiply by that by r cosine of theta plus sine of theta, right? You can do like that, right? So if you carry out the multiplication and you repeat this recurrence relationship, you can find you can prove this, right? And that is example 4. So now let's do some base cases, right? Well, you can really prove this by induction, but over here we are not going to prove it by induction. It's too much work, really, and this is not really a proof class. No, not too much of a discrete mathematics class. You can learn about all the induction over there, right? So let z equal to its polar representation, right? And well, let's do what we did, right? It's equal to z, right? So z1 equals z2 equals to z. Then we can define it as the following manner, that is z squared, that is equal to, or really just, if you carry out the multiplication, that is equal to cosine theta plus theta, right? And plus I sine of theta plus theta, and well, that is just equal to sine, or sorry, r square cosine 2 theta plus I sine of 2 theta. Well, we didn't really have to do a multiplication over here because we've already did it over here, right? We did it over here, really. So we're really just using corollary. And now right, so maybe we do you see z cubed, right? That is equal to z squared. See, now we're really just carrying out the recurrence relationship exactly as how I predicted it. The textbook now is doing some examples to just give you the base cases, and now and they do have a very funny corollary to this, right? Now, well, Z3 can be defined as this following manner, right? Really just, 3 square and plus I of sine 3 theta, right? Is this too small? I hope it's not too small for you, right? So this is Z3. So the corollary to this is that, well, what if we have something like this, right? Z is equal to, well, I don't want 2, I want a negative number. What does this mean? This means that it is 1 over Z squared, right? And funny enough, well, this can be written as really just, well, let's rewrite it in this form, right? And then we use a corollary, no, we use a theorem, and that is equal to cosine of, well, negative theta. And because we can really pull out the sign, but you can pull out the negative sign, but I'll just keep it in the sine function, right? Like that. Okay. And just well, let's do it over here actually. Sorry. Well, what if z to 0, right? Well, what is z to 0? It's really just equal to 1, because anything to the power of 0 is 1. Well, let's prove it, right? We have r0, well, that is 1, right? And then you have well, cosine of 0 plus I sine of 0, right? That's really just 1 times 1 times 1 plus 0. That is just 1, right? and now let's do another example. So let's do example 5, right? Example 5, power of a complex number. Well, it's example 3 over there in the textbook, but I do it my way, right? So let's compute z to the power of 3, right? But what is z? Our z is, well, we did already, really just root 3 minus 1 minus I, right? So now let's do it. Recall that the polar representation of z, right? Polar representation of z, that is z equals to 2 cosine of 7 pi over 6 plus I sine 7 pi over 6, right? And, well, we know our r is equal to 2, our theta is equal to 7 pi over 6. Now invoke the theorem. Well, sorry, before we invoke the theorem, we know we want to calculate the third power, right? So we want to invoke the theorem. We say negative root 3 minus I to the third power. Well, that is really just 2 to the third power of cosine of, well, 3 times whatever's in here. That's 7 pi over 6, right? Plus I sine 3 7 pi over 6, right? And that is equal to 2 to the third power 8, right? And you have cosine of 7 pi over 2 divided by 3, right? And you have, well, 7 sine 7 pi over 2, right? And, well, we know sine goes to 0. No, we know cosine equals to 0, really. So if you draw like that, right, and sine of 7 pi over 2, you can subtract 6 pi, that is over here, right? This angle over here, and we know cosine is equal to 0, so really this goes to 0, right? And now we can write it as z to the third power, that is equal to negative 8i, right? So this is our answer, right? Well, in this term it's just negative 1. right? And now we want to introduce another theorem. It is De Moivre's formula, right? De Moivre's formula. Well, it's defined as the following, right? Now, and when z is equal to cosine of theta plus I sine of theta, well, that implies r is equal to 1 because we see now r disappeared. Well, that's really just multiplied by 1. That's the multiplicative identity, right? So the modulus of z that is equal to r, really that's equal to 1, right? And now if you would combine it with, you know, our previous theorem, which is this one, the power, integer power, right? Integer power theorem, really you want z to the, I do z to n power, right? That is equal to cosine. What is z? Z is cosine plus I sine theta, right? To the n power. That's just z to the n power, right? But our r is equal to 1, and 1 to the n power is still 1. That is cosine of n pi plus I of sine n pi, right? Because, well, we can just distribute it, multiplicative identity, right? And this result is known as the De Moivre's formula, right? De Moivre's formula, and it's useful in deriving certain trigonometric identities involving cosine to n power, to n theta, cosine of n theta, cosine n theta and sine n theta, right? Really. Now let's do another example. That's example of 6, right? Now if we'll recall that really our z is equal to this number, root 3 minus I, negative root 3 minus I, right? And we know that theta, which is the argument, not the principal argument, right? Really, that is equal to 6. And then, well, cosine of theta, right? That is pi over 6. That is equal to root 3 over 2. And, well, what is sine of theta? Sine of theta is equal to 1 over 2, right? And, well, if we wait, is I correct? No, I don't think it's correct. Sorry, because it's not written explicitly over there. But we can try to figure out what I is, right? We know theta is equal to this. Well, if we theta, well, then our x, right? Our r is equal to 2. Our x is equal to root 3. Really, this is just this number over here, right? That is equal to root 3, and this is our root 3, and the y is equal to 1, right? Really, so our z is equal to root 3 plus 1, I think, right? It should be correct, I think. Really, because our pi was what was it, 7 pi over 6. Really, we just flipped it around, right, to this over here. So we just have to remove the negative signs. And now if we want to use De Moivre's identity, well, we can write a cosine, right? This is our cosine, and write our sine over here. Well, how about we write the I in the back, right? And let's raise it to the third power. Really, that is just equal to cosine of 3 theta. So 3 theta equal to cosine of 3 multiplied by that. right? Multiplied by our theta plus I sine multiplied by 3 multiplied by theta, right? That's equal to, well, cosine of pi over 2 plus I sine of pi over 2. That is equal to I, right? Really, because, well, this becomes 1, this becomes 0, 1, 0, right? And now, that is the end of 1.3.